Hello, everyone in physical science or in physics. Today I am going to be covering a more complicated topic and looking at complex or combination circuit calculations today. Okay, so we are going to be looking at this circuit here. I'm going to change one minor thing on here, and that is change this to 120 volts instead of 12 volts to make it a little bit easier to deal with numbers. And then we're going to get started here. Okay, so we're using this circuit diagram to figure out what are, fill in our blanks here, to be able to see what our voltage and current are through all of our four resistors here, as well as a total current and resistance as well. Okay, so first off, we look at our circuit and we can tell that it is a combination circuit because it has both things in parallel. There's resistors in parallel as well as things in series as well. So we know that this is indeed a combination circuit. Okay, and with combination circuits, they have to follow rules for both series and for rules in parallel. So let's write those down here. So if we remember, our first rule deals with voltage. So voltage in a series circuit, voltage lowers with each resistor, but adds to the total. Okay. The second rule for series is current. So if we look at that says that current, so it basically says that current is the same in all series resistors. Okay. In other words, all parts in series share the same current. Okay. Our third rule about resistors is that all resistors add up to a total resistance. Okay, so this is for the stuff in series. For the stuff in parallel, our first rule deals with voltage. So voltage is the same in each branch. Okay. And I'm going to add a little bit on here for combination circuits, which is it is the same as the battery or the remainder after after you consider series circuits, or after things in series resistors. Okay. So it's the same as the battery in normal conditions if it's just a parallel circuit. Otherwise, it's the remainder of the voltage split between the branches once you consider your series circuits, your series stuff you have in the circuit. Okay. Our second one is about current. So your current, all branch currents add up to the total resistance, or the total current. Sorry. Okay. And then lastly, our resistance in parallel, your total resistance is less than total. It normally follows the less than your total or sum of resistors. Usually follows the equation RT equals 1 over 1 R1, 1 over R2 plus 1 over R3, etc. for however many resistors you have. Okay. So this is without Ohm's law. That's how you would find it for your things in parallel. So I'm putting these down so that we have something to look back at, something to reference in case we get stuck anywhere. So let's look back at our diagram here and look at our chart, at our little charty chart we have to fill out. And I have filled in already that V, our total voltage, is 120. So that's our battery voltage. And then I have resistance numbers for our 1 through 4. And we can actually put those numbers in up here so that you can reference it later. R1 is 10. So that's up here. 20 is R2. R3 is 30. And R4 is 40 ohms. Okay. Next, what you have to do is realize what's happening here in your diagram to see what you need, like to focus in and lay out what you need to do or find first. Okay. So at first you might go voltage lowers with each resistor, but you might start looking at your rules and figuring something out. So some people might, go straight over here and say current is the same in your series, here, which means all parts share the same current. You might say that's great, but that's just for your series. We don't know what that is yet. Same with like your voltage over here. It says it's the same in each branch. It's the same as the battery or after the series resistors. So we can't enter in over here like normal what we would do for our voltage. It's not 120 because we have to find out what the voltage is here first. But this tells us one thing. It tells us that certain boxes will be the same depending on your rules. So give me a second here. I'm just going to grab some highlighters. So based on your rules here, your first one says that your voltage lowers with each resistor, but adds up to a total. Okay. We don't know quite what to do with that yet. 2 says current is the same in series. All your parts share the same current. So all your series circuits or series resistors are going to share that same current, which means that the current in both of your resistors in series, which is 1 and 2, are going to have the same number. So the boxes here for resistor 1 and 2 are going to be the same because they are in series. Okay? Okay. All resistors add up to a total resistance. So that means we can add these two up. But this also means, if we think about it, our two parallels, once we combine them, they're considered a series resistor. So we need to, if we find the resistance for these two together, we can treat them like a series resistor. Okay? Which means once we find the resistance in total here, we can add it with these two to get the total resistance. Okay? And we can do that here in a little bit. Let's see what else we can do on here. For our fourth one, it says voltage is the same in each branch. This is the same as the battery or the remainder after the series resistors. So this means that if we find our voltage in these two, then whatever remains is going to be shared equally in these two boxes, meaning that the number that we get for the remainder after our series, which are R1 and 2, for our parallels, it's going to be the same. So whatever we put in these two boxes will be the same number that we put in these boxes that are in purple. Okay? So far we know that the numbers here and here are going to be the same to each other, meaning that the numbers in the purple will be the same and the numbers in the yellow will be the same as well. Okay? We still haven't filled anything out, but now we know that we have some clues for these boxes. And we have a good place to start for the other ones. If we look at 5, let's just go through the rest of our rules here. So 5 says all branch currents add up to the total current. So this should mean that once we add these two together, they'll equal the total. And the only way we'll find the total is if we find out these. So we can't do anything with current here yet. So we can't do anything with voltage, can't do anything with current. That leaves resistance. And with our 6, total resistance is less than your total or sum, and uses this equation. Okay, so we're going to use the combination of both of these rules to figure out our total resistance first. Okay, and I am going to be using this equation since I don't have any way to find our current here. So, like I said, we need to follow both of these rules. So that means that if we follow our series one, so we have R1 and 2 in series, those resistances add up to a total. So we can add these together and they are a total of 30. And like I said before, we also need to follow this rule for our parallel resistors. So we need to follow this. But once these two, we find the resistance of both of these, we treat that total like a series resistor, like whatever is remaining to add together. So let's find the resistance between just our parallel, which is our 3 and 4. So RT of our parallel stuff, and like always, I'm going to use the bottom part only and then flip it upside down later. So 1 over 30 plus 1 over 40 is going to be the resistance in total of our parallel area. Okay. So let's find the common denominator here between these two. And easiest way to do that is times the front two together. So 3 times 4 is 12. Add a 0, which is 120. So let's convert this here. So we want 120 as our bottom number. So 120 divided by 30 is 4 times. So each of these needs to be times by 4. And so 1 times 4 is 4 up here. And 120 divided by 40 for this one is 3. So each side here gets times by 3. That will give us 1 times 3 is 3, and 120 on the bottom. We add these together to get 7 over 120. Flip it upside down on its head. 120 divided by 7 is going to be 17.14 ohms as a total resistance in it for R's 3 and 4. Okay. So like I said, we can treat this number here, since it's the total between both of these, like a series resistor. And so now all we have to do is add up those two numbers with our total resistance that we had there. So 17.14 plus 30 is 47.14. And that gets us our total resistance of 47.14 ohms. And you could just round that to 1 if you wanted to, 47.1. Okay, so that is how we used our rules to figure out that we had to use, or what we had to figure this box out first. This is our first box. Once you do that, once you have this one clue, now we can start filling in other boxes, because as you remember before, we now have 2 of the 3 parts of Ohm's law to help us out. So with this, we can now use Ohm's law to figure out what our current total is. So if I draw my triangle of our equations, V on top, I and R on the bottom, we are looking for I total. So I in total equals V over R. Then we can put our numbers here in. So it's 120 volts divided by 47.1. I'm just going to use 47.1 ohms. So 120 divided by 47.1 is going to get you 2.55 amps as our total. Okay, that's our total ampage take a look back at your rules if you're lost. Once you find this out, there's something that you can fill out, which is bingo bango. Current is the same in your series resistors. All parts share the same current between all series resistors. This one and this one are going to be the same current as the total, which in this case is 2.55 amps. Now we can't say that about these, and that's because all branch currents add up to your total current for these, which means these two boxes here added together will equal 2.55. Okay, but we can't figure that out yet because we don't have this yet. However, now up here in our series resistors, we have both two of the Ohm's law to find V. So what we're going to do is use Ohm's law again to figure out what V is. In this case, V equals I times R. So V equals IR, which is basically just 2.55 times 10. And those of you who already know math, that's going to be 25.5 volts. Okay? And then we can do that for down here as well. 2.55 times 20. Don't forget that this is a different number here. And that gets us the number of 51 volts. Now you might be a little confused and go, but wait. Aren't these two supposed to add to a total voltage? 51 plus 25.5 is clearly not 120. But like I said, both of our parallel, once we put them together, are going to be treated as a series resistor, which means that whatever, and it's according to our other rule up here, voltage is in the same in each branch. Like we said, whatever number we have, here is going to be the same in each box. Which means that whatever is left over after we consider our series resistors is going to be the number we put in here. So we started at 120 volts. Through one resistor, we got rid of 25.5 volts. And through the second resistor, we got rid of 51 volts. This leaves us with a total of 43.5 volts left to fill up to 120. That is what number goes here. And because these both have the same voltage in each branch, both of these are going to be 43.5 volts. Okay? So far we found the resistance, we found the total current, we found out what our current in our series resistors were. We then found our voltage in our series, and then the voltage in our parallel. From here now you can realize that you can figure out, because now we have 2 of Ohm's law for these, now you can fill out your current in your parallel circuit resistors. And so we just do our I equals VR again, V over R. So our current is going to be 43.5 divided by 30. And then down here it's 43.5 divided by 40. That gets us 1.45 amps here. And 1.09 here. Now you might be looking at those numbers and going, huh? But if we look back at our rule for current in parallel, it says all branch currents add up to the total current. If we take 1.9 and add it to 1.45, we see that the number is very close, if not exactly our total. So in order to check if these numbers here that you got are right, you have to take them and add them up to see if they equal the total. Okay? But after you do that, you're done. That's it. You did it. You filled out all your boxes and you're good to go on combination circuits. One thing I will have to like caution you on is make sure when you're looking at these, this is a simple combination circuit. The more branching paths you have, the more complicated it gets, but all you have to do is make sure you follow make sure that all of your rules here are followed for your combination circuit. Okay? And you have to just break things down logically. I know it seems complicated. That's why they're other than combination, they're also called complex circuits. I know this seems complex and it seems hard, but all you have to do is kind of break things down and figure things out while following your rules. Okay? I know this one was long. I might try doing another one to show you how it's solved. But I'll do that in another video since this one was long enough. Okay? But in summary, what I did was I first looked at my diagram, labeled the stuff on it, determined which of my resistors were in series and which ones were in parallel so that I knew which rules to like attribute to which resistors. So I knew why I had to use this equation for this one and why I could just add these ones together. After that, then once I determined that I had to find the resistance was the thing that I could find first. After that, once you start filling in boxes, it becomes a lot easier. Okay, so once I found out that I could do resistance first, I used that to then find the next closest thing that I could find. And usually you use Ohm's law. If you have two of the three, that's how you continue your path. And at any time that I was lost, I would stop and read my rules here to see if I couldn't get a clue as to what to do next. These clues or rules also help me to realize things about my boxes that I had to understand. Things like, oh, the current in both of these is going to be the same as the total. Or, oh, these two added up together will be the total current. Or, oh, these three together or these three together are going to equal the total. Or, oh, the voltage in both of these has to be the same because it's the same as the remainder after we get it sucked up by these guys. Okay, so realizing that these turned out to be the same number and these turned out to be the same number really are good hints. Okay, but that's how you figure out combination circuits. Sorry, this one was a bit on the longer side. If you have questions about this for me, let me know. Otherwise, I will see you in the next one. Take care, everybody. Don't let this be too complicated in your brain. It's just something you have to think about. Okay? I'll talk to you all later. Take care. Bye.